Now let's put together what we learned in 3.2 about our polynomial functions, 3.3 working with synthetic division and how that helped us determine solutions and zeros. Let's put that together to find all the zeros of a polynomial function. We'll use the rational zeros theorem to help us determine a list. We'll find some zeros, we'll solve some equations, and we'll use the linear factorization theorem. So here's an interesting thing that I pulled from your book. We're going to incorporate several techniques for finding the zeros, but here is the format that your zeros can possibly come in. So here is a polynomial function, and here are the various kinds of zeros that we might see. We don't have to look at all this part here, but I want you to see the different types of zeros for now. You might have rational zeros, and rational zeros are those that can come in a whole number form or a fraction form. Those are our rational zeros. We may see irrational zeros that come about from the quadratic formula, which may involve square roots of numbers that aren't perfect. So we might see rational zeros, we might see irrational zeros, and all of those are part of the real number system. Those are our real zeros. We may see those of the type that are imaginary or complex zeros. Those type will involve an I, and they are non-real zeros. These guys that involve the I come again from the quadratic formula. Where does an I come from? Let's just do a quick little review. If we had the square root of a -4, earlier we called the square root of a -4, it was undefined because we were only working in the real number system. You're going to have to forgive me, I can't write today. Alright, square root of -4 was undefined. Now, since we're working with complex numbers and we're working with non-real zeros, the square root of -4 will be interpreted as 2i. Remember, the I comes from the fact that there's a negative under the radical. That's where our imaginary unit comes from. So if we see something like the square root of a -25, we would call that 5i, our imaginary or complex zeros. They'll come from the quadratic formula. Remember, we'll get the square root, and if the number underneath is negative, it's an imaginary number. Another important thing about the unit of I is this. Very important, we have to remember the value of I squared. I squared is equal to a number -1. Some quick notes about complex numbers. So these are the types of zeros we might get. The first thing we're going to look at is the rational zeros theorem, something that will help us determine these guys right here. Let's take a look at it. It's going to be a tool that we can use to make a list of possible rational zeros. It's not going to just give us what the zeros are, it's going to be a list of possible zeros. And from that list we have to determine which ones in that list are actually our zeros. So here's how we'll construct the list. Given a polynomial in its regular form where it's in descending powers, all the coefficients here are nice integers, what we do is we take the constant term, that term at the end, and list all the factors of it in the numerator. Then we take the leading coefficient, this guy, and write all the factors of it in the denominator. Then we take every possible combination of the numerator factors divided by the denominator factors. And I mean every possible combination, meaning plus and minus. Sometimes it'll give you a pretty extensive list, but guaranteed you'll be able to find some of the zeros in that list. So let's list them all, and then we'll verify it on our calculator. So let's list out all of our factors, and it comes in the format of P divided by Q. So let's list all the possible P divided by Q's. P's come from the constant term here, 4. All the factors of 4 will go on the top. and all the factors of the initial term, actually it's a negative 1, but we'll just take it as a 1, all those factors will go on the bottom. All the factors are 4, which means all the numbers that divide evenly into 4 are the numbers 1, 2, and 4. All the numbers that are factors of 1 are just 1. Now if I take every possible combination of the top numbers divided by the bottom numbers, that would be plus or minus 1 over 1, 2 over 1, 4 over 1, which is just plus or minus 1, 2, and 4. That's the list. Now that's actually 6 numbers, the positive versions and the negative versions. What we would need to do is we could try using synthetic division to find out which ones from this list would work in that polynomial function. Right now, let's just verify using our calculator that the zeros for that function are actually in that list. So let's pull this up. Let's go to y equal, clear out what was already there, and let's type in this function. Where is it? Negative x to the 4th plus 3x squared plus 4. Negative x to the 4th plus 3x squared plus 4. And let's graph it. Now we see this nice little W thing. We see it's crossing the x-axis at 2 spots. Let's see what they are. Let's go to the table. And there's one spot. It's crossing at -2. That's one of our zeros. I suspect the other one to be at 2. Yeah, because of the nature of it being an even function, symmetry across the y-axis, I have a 0 at -2 and a 0 at +2. The question to you is, are those numbers found in your list? Yeah, they are. So on the calculator, we find -2 and +2 are zeros. And actually, these are from the list. These are found in the list. Now, there's actually 4 zeros for this polynomial. The degree is 4, so there's actually 4. But the calculator will only tell us the real zeros. This problem only has 2 real zeros. What does that tell me about the other 2? Because there has to be a total of 4. If 2 of them are real, if we go back to our little statement up here, if 2 of my zeros are real, what's the only other category the other 2 could fall in? They're non-real or imaginary, complex imaginary zeros. So I could make a statement here that I have 2 real zeros and 2 complex imaginary zeros. These can't be found on a calculator. The real ones can be found on the calculator. So if you're given a list, how do we determine which values in the list are actual zeros of the function? We'll use synthetic division to test each value, and what we're looking for is a remainder of 0. If we find a remainder of 0, then that value is a 0. So let's kind of play this game with this function here. Let's work on getting that list. And it's going to be all possible values, positive and negative, of this constant at the end. All the factors of 6 are 1, 2, 3, and 6. And all the factors of the coefficient up front, 1, are just 1. So that one's not too bad. Let's set up the list. It'll be plus or minus 1, 2, 3, and 6. Now what we need to do is just start using some synthetic division with that list and find basically the needle in that haystack, the zero or zeros that are in that list. I mean, there's no special way to go about this. The coefficients are 1, 2, -5, -6. Now what we have to do is pick the number in the box from this list, and we're hoping to get a remainder of 0. I'm going to try 1. So if I put in 1, 1 times 1 is 1, I get a 3. 3, -2. Nope, that's not going to give me a 0. So 1 doesn't work. Kind of scratch that out, and I'll try a different number in the box. 2. 2 times 1 is 2, I get a 4. 2 times 4 is 8, subtract that, I get a 3. Wow, I found one. I didn't expect to find it quite so soon. So I'm working in my list. +1 didn't work, so I jumped over to +2. When I put in +2, let me make sure my arithmetic is okay. +3, yeah. So from my list, I find one of my zeros. Now I could continue in my list trying the 3 and the 6, then the -1, -2, -3, -6, but that's a lot of spinning my wheels when I'm left with a quadratic, that magic quadratic at the end. It's an x² plus 4x plus 3. Anytime I'm left with a quadratic, I'm going to stop in my list and work on that quadratic, and I see that this is a quadratic that's going to factor. X and x, 3 and 1, positive, positive. Now again, I could have continued in the list. It was just easier for me to factor that quadratic and get an answer of -3 and an answer of -1. So what are all the zeros for this for this polynomial function? We get a 2, we get a -3, and we get a -1. Now we could go to our calculator and verify that those are indeed the zeros. Let's just do a quick calculator. And I have x³ plus 2x² minus 5x. Let's see if I typed that in right. No, I didn't. Should have been a -6 at the end. I knew I made a mistake somewhere because I found 3 zeros algebraically, but I'm only seeing 1 on the calculator, so yeah, I typed this in wrong. That should have been a -6. Nope, went too far. There we go. Now let's see if it's going to show all 3 that we found algebraically. This looks like a -3, a -1, and a 2. Let's see if we can verify that on the table. -3, a -1, and a 2. And by hand it was a -3, a -1, and a 2. So yeah, that kind of verifies that our work algebraically was correct. We found all the zeros. Let's do the same thing for the next one. Let's work on calculating or making up our list. Plus or minus, the bottom value factors go on the top. The initial coefficient factors go on the bottom. Now our list isn't very extensive. It's plus or minus 1 and plus or minus 3. 1 over 1 and 1 over 3. And we're looking for 3 zeros, but we're just going to see if we can find one from that list. I don't know what that number is. Let me see what that number is. (7x²). So 1, 7, 11, negative 3. Drop down the 1. And let's pick something from this list to put in the box. I'm just going to start with 1. And 1's not going to work. When you see you're not going to get a remainder of 0, hit the next value. Let's try 3. Nope, that's not going to get me a remainder of 0. So let's try a different one from the list. Let's try negative 1. Nope, that one's not working. Let's try negative 3. Aha, there it is. So I had to go through all of the values in my list before I found one that worked. Well, that's the first needle in the haystack. Since all of them were tried and I only found one rational 0, that tells me the other ones are either irrational or complex. But I can get that from that final quadratic. X squared plus 4x minus 1. Well, this is one that's not going to factor, so let's pull out the quadratic formula. Negative 4 plus or minus the square root. 16 minus 4 times 1 times negative 1. All over 2 times 1. Negative 4 plus or minus the square root of 16 plus 4, which will be 20. And that radical reduces. 20 is the same thing as 4 times 5, so it's a 2 square root of 5. And this final result, since these three numbers are all divisible by 2, that quadratic formula result can be reduced to negative 2 plus or minus the square root of 5. These are not rational zeros, and so they won't be obtained from the rational zeros theorem when we list out all the rational zeros. Only rational zeros will come from the list. If you have irrational ones, they'll come from the quadratic formula. So let's list out our zeros. The one we found, negative 3, which came from the list, and the other two, negative 2 plus square root of 5, negative 2 minus square root of 5. I was looking for 3. I found all 3. There's my list of zeros. Now sometimes this rational zeros theorem, when you're working on that and getting your list, the list can be quite lengthy and it can take a really long time to get through that list. So I would prefer this different approach to finding zeros. What we'll do is we'll graph it on our calculator and we'll find our rational zeros, such as the ones listed here. We know the ones that are rational. We'll find those from our calculator. Instead of having to go through that list, we'll just grab them from the calculator. Then we'll do synthetic division to get it down to a quadratic, and then do what we usually do with the quadratics, either factor or use the formula. So this method is replacing writing out that list. Instead of writing the list, we'll go straight to the calculator.